This is Chemistry 3053, and today we're covering organic chemistry, radical reactions, chapter 10. So this shows you how the chapter is going to be broken down. The first part we're going to look at just radicals themselves, their structures and stabilities, common patterns in radical mechanisms. We're going to start with the chlorination of methane. Then, after that, the next video will include thermodynamic considerations for halogenation reactions. And this, again, is going to be halogenation of alkanes. And then we're going to look at the selectivity and the stereochemistry of those reactions. Then we'll look at allylic bromination, the atmospheric chemistry and the ozone layer. This 10.8, I won't emphasize so much, and 10.9 because you're not going to see a lot of that on standardized exams, and I think that this is something that you're very interested in, is doing well on standardized exams. And then the last class period, we'll look at radical addition of HBr, anti-Markovnikov addition, which we've previewed in an earlier chapter. We'll look at radical polymerization, radical processes in the petrochemical industry, and halogenation as a synthetic technique. So let's start. So free radicals, let me just mention that nowadays the term radicals and free radicals mean the same thing. This term free radicals you won't see so much because decades ago, the term radical was used instead of substituent. So now that we're using the term substituent to mean a methyl group on a molecule, we don't have to talk about free radicals. So free radicals simply means a group, a substituent that is free and not attached to anything. So nowadays the word radical and free radical mean the same thing. Those terms mean the same thing. So radicals form when bonds break homolytically. So remember that is a single bond that contains two electrons. It breaks. One electron goes with one part. The other electron goes with the other part. And so this is called homolytic bond cleavage because the two parts that are formed when the bond breaks, the two molecules that are formed, are alike in that each contains an unpaired electron. Notice the single barbed arrow, sometimes it's called colloquially a fishhook arrow. That means the same thing, single barbed and fishhook, are used to show the movement of one electron. The double barbed arrow shows the movement of two electrons. Single barbed shows the movement of one electron. As you know, we've covered that already. We've covered that carbocations are planar. They have an empty p orbital. The carbon is hybridized, sp2 hybridized. We haven't covered so much that carbanions, this is the molecule that in which there are two electrons. Instead of having an empty p orbital, you have two electrons in that orbital, and that carbon that bears an orbital that has an unpaired or an unbonded pair of electrons, this orbital is filled, and it is an sp3 hybridized orbital because that carbon is sp3 hybridized. This is trigonal pyramidal. Notice how the bonds are no longer lying in the same plane. This is trigonal planar. Notice all of these bonds are in the same plane. And so there's a little similarity in that carbon is bonded to three other atoms. Here carbon is bonded to three other atoms, but here carbon has an empty p orbital. Here carbon has an orbital that has a pair of electrons, carbocation, carbanion. This will bear a positive charge. This will bear a negative charge. Now, radicals don't have either of these because radicals have a single electron in that orbital. And so the radical is usually drawn as being similar to a carbocation, planar. And that would be trigonal planar. Here, the 3 bonds to carbon are lying in the same plane, sp2 hybridized. And so instead of having an empty p orbital, you'll have an orbital that contains just 1 electron. Both lobes together just contain 1 electron. But sometimes some of the radicals can actually be have a very shallow trigonal planar structure, trigonal pyramidal. So this would be like a pyramid here, but close to planar, not as pyramidal as the anion that you saw just a minute ago. See, this is much more of a pyramid, and here this is closer to a plane. And these can interconvert very easily, and so you won't have any stereochemistry preserved. This essentially functions as if it were planar, because the interconversion, the flipping of the carbon, the stereochemistry flips so rapidly that you don't have any stereochemistry preserved there. And so here, this is sp2 hybridized. This would be sp3 hybridized, but you would consider it almost planar. So any stereochemical considerations, you would need to regard this as planar or very close to planar. So radicals don't contain, they don't bear a charge. They're not positively charged or negatively charged, but they are still electron deficient because the carbon is surrounded only by 7 electrons. And so, since it's electron deficient, in some cases, the radical behaves as a cation. And so that's convenient because you can associate those instances with what you learned about carbocations. So here, for example, you have methyl radical, a primary radical, secondary radical, a tertiary radical. That's because here the carbon is attached to no alkyl groups. Here the central carbon that has the unpaired electron is attached to 1 alkyl group. Here the carbon that has the unpaired electron is attached to 2 alkyls, and here the carbon that bears the unpaired electron is attached to 3. And this has an increasing stability. The carbon that is the radical center bearing 3 alkyl substituents is the most stable, exactly as if it were a carbocation. So this trend is exactly what you would see, or what you do see, in carbocation stability. So this trend will be the same. If you replace the dot with a plus, you'll have exactly the same trend. So that will make it a little easier for you to remember, and you just remember that they have that similarity because they are both electron deficient species. Now, the bond strength is inversely proportional to the carbon radical stability. So the more stable the radical is, the easier it will be to break that bond and go to that radical. And so we just saw that the methyl radical is least stable, and so that means that it's going to be hardest to cleave that CH bond homolytically and lead to that methyl radical. And so the bond strength is strongest over here and highest. It has the highest number over here because the tertiary radical is the most stable. It will be easiest to homolytically cleave that CH bond, and that means it takes the least amount of energy to cleave or break that CH bond and go to the tertiary radical. And so you see that reflected here in this decreasing bond dissociation energy. That's what BDE stands for, bond dissociation energy. Similar to the cations, the radicals can be stabilized by resonance delocalization, and so you are simply, instead of thinking of it as spreading out the positive charge, here you think of it as spreading out the unpaired electron density. And so here you have unpaired electron density, and now you're spreading out the unpaired electron density. So you're going to have some unpaired electron density at carbon 1 and some at carbon 3. Here you can see it in where the unpaired electron is drawn. And that's going to be true of all of the allylic molecules. And if you want to draw between the two resonance structures to help you visualize those two resonance structures, which are drawn to represent the single structure of this molecule. Remember, these are two resonance structures that are drawn to explain the single structure of that molecule. You can do that by using these single barbed arrows showing one electron moving in, one electron from this pi bond moving in to form your new pi bond. The other electron from that pi bond moves out to give you the unpaired electron. So you have to use the single barbed arrows to show that. And so, just like with carbocations, the more resonance structures you have, the more the unpaired electron density will be spread out. And so here we've drawn 1, 2, 3, 4 different resonance structures because, well, no, I guess this one is different because here the pi bonds have moved around in the benzene ring. So you have 5 different resonance structures. And so the unpaired electron density is more spread out around the ring. And so that means that the benzylic radicals, this radical, drawn either way here, these are more stable because the unpaired electron density is spread out over more atoms. And you can see that stability reflected in the amount of energy that is required to break that bond. Notice, remember, we said that the butyl radical, the tert-butyl radical, where you will be generating a carbon that is tri-substituted, the carbon bearing the unpaired electron is tri-substituted. We said that was very stable. But if you break the bond to lead to the allylic radical, it's even less energy required. And so that means this is indeed more stable than that. And so the radical that would form by breaking this bond here takes still less energy. And so that tells you that the benzylic radical is even more stable than the allylic radical because less energy is required to break the CH bond to lead to that radical. Vinylic radicals, on the other hand, are not stabilized by the pi bond because here that electron that resides on carbon, once you break this bond, is not resonance stabilized. That electron is in an sp2 hybridized orbital. And so you can see that reflected by a higher bond dissociation energy. And here this is compared to that of the ethyl radical or the allyl radical. Notice that these are both less than the cleaving the bond to lead to the vinylic radical. So 464 has the highest energy because cleaving this bond would lead to the highest energy or the least stable radical in this group. So you don't want to confuse the vinylic radical and the allylic radical just because there's a double bond in both. Now, there's patterns in the radical mechanisms that will help you to remember and be able to predict these radical mechanisms. So you recall when we had the carbocations, you remember that if you had a positive charge next to a a carbon that's bearing 3 methyls, you could have a 1,2 methyl shift where one of these methyls could migrate and the positive charge would move to the tertiary carbon. You will not see that in the analogous radical molecule. You will not have the methyl shift. Okay, so that is one difference between carbocations and radicals. You will see a lot of similarities, but this is not going to be one of them. Now, let's look at 6 common steps that you see in radical mechanisms. So you've already seen one, which is the homolytic bond cleavage. You see 1 electron goes with each molecule that's generated, and you see the unpaired electron on each of the molecules. So this is homolytic bond cleavage because the 2 molecules that are generated are alike in that they each contain an unpaired electron. Notice that this says heat or light. That little triangle up there, you probably already know it means heat or light. And so that can be a key for you when you're trying to look at reagents that are given and you're trying to figure out what reaction might be occurring. If you see heat or light drawn just like that, it's usually a radical mechanism. Not always, but usually. If you see light, that can be a good clue to you. Just seeing heat with other reagents, that doesn't necessarily mean that it's a radical mechanism because a lot of reactions in organic chemistry require a little bit of heat to get the reaction started. And so this homolytic cleavage, this is very often the first step that you see in a radical chain mechanism. And I would say that most of the reactions that you're going to see that are radical reactions are going to be radical chain reactions. And so a step like this, which involves a homolytic bond cleavage, is going to be the first step in that mechanism. And then once you have the radicals generated, then they'll do other things. And those other things will be the subject of these remaining steps. And we're going to see 5 more steps. Usually the first one will be this, like this. The first step will be like this. And then you'll see some of these others in various combinations. And so one of the things that it could do, the radical, once it's generated, is it could add to a pi bond. So you can see the unpaired electron forming this CX bond. You use the unpaired electron on X, use one of the electrons out of the pi bond, and the other electron in the pi bond moves over to reside on carbon. So this is addition to a pi bond, okay? And you're forming a new bond here. Or you could use X dot and do a hydrogen abstraction. So here, the unpaired electron on X is going to be used to form this bond between X and H, and the other electron in the X and H bond is going to come from this bond between H and R. So here you move one of the electrons out of the HR bond, and now you formed this 2-electron bond right here, and the other electron in this HR bond moves off with R. And so this is called a hydrogen abstraction. Notice that I didn't say proton, because a proton is H plus. A proton is bearing a positive charge. This is not going to bear a positive charge. It's taking an electron with it. When X dot means the X radical. When X dot abstracts H dot, it takes an electron with it. So that's where you get the 2 electrons. So this is not abstracting a proton. It's abstracting a hydrogen atom, and that means H along with one of the electrons. You have to have 2 electrons to form that H-X bond. One comes from here, one comes from there. And so this is hydrogen abstraction. Now, you can also have halogen abstraction. So here we've got R dot. It's another radical. It doesn't have to always be X dot. So here we've got R dot that is going to abstract X dot, where X is a halogen. So this is analogous, exactly analogous to the hydrogen abstraction, except down here you're having a halogen abstraction. The arrows drawn are exactly the same. R dot moves in, it forms a bond to X. You use the electron that is residing on R. You use one of the electrons out of the XX bond. The other electron in the XX bond departs with X. So R dot abstracts X dot and forms RX. 2 electrons, one comes from here, one comes from there. The other electron moves off with X and forms X dot. So these 2 will be easy for you to remember, because here you're doing a hydrogen abstraction, down here you're doing a halogen abstraction, and they're very, very similar. You need to look at these. If it's not already obvious to you that they're similar, you should look at them until you realize that they are similar, because you're going to have 6 different reactions here. And it will be easier for you to remember them if you can remember them in groups. And they will be in 3 groups. And I will show you the similarities. So you can remember them as pairs. Remember them as pairs in your mind. And this is one of the ways that you can pair up reactions 3 and 4, or steps 3 and 4, to remember that these 2 are the same. Now, here, what you're going to see on the next slide, look at 6. Let's skip to 6. Coupling, the reverse of the cleavage. Can you see this? X dot and X dot are coming together to give you X2. And so this is the reverse of the cleavage. You see? The reverse is X dot and X dot going to X2. And so that is reaction number 6. Okay? Elimination is the reverse of addition, where you've got this radical, you have the departure of X dot and the formation of a double bond. You can draw that by using one of the electrons from this carbon-carbon bond departs with X. The other electron moves in to form the pi bond. And look, you see here you've generated X dot and an alkene. On the previous slide, you can see you started with X dot and an alkene. So this is the way to remember these. You don't have to remember all 6. You can remember that step 1 and step 6 are opposites, in that step 6 is the reverse of step 1. Step 5 is the reverse of step 2. And then remember that 3 and 4 are the same, except here you've got a hydrogen and here you've got a halogen. And so that is the way that you can remember 3 items instead of 6 by grouping them in your mind, and it's easier to remember. Now here, this appears in your textbook, and here it's drawn for you to visualize it, to help you visualize it. And here you can see you've got the cleavage and then the coupling. They go in opposite directions. And here you've got addition and elimination going in opposite directions. But reactions 3 and 4 were not the reverse of each other. This one is hydrogen abstraction and this one is hydrogen abstraction. Halogen abstraction was number 4, and it's not shown on here. You'll have to just remember that hydrogen abstraction and halogen abstraction are the same. These two don't demonstrate halogen abstraction, because in each case you're abstracting a hydrogen. So halogen abstraction, which was the 4th critical reaction that you needed to remember, is not on here, even though this is supposed to be a review. So, you'll just have to remember the halogen abstraction as being similar to this. So, what I just discussed with you was an analysis according to the mechanisms of those steps. There's another way to analyze and that you must learn to analyze the steps of a radical chain reaction. And in this case, the steps are grouped according to their functionality, not according to their mechanisms and the arrows that you must draw. So here, the steps in a radical chain reaction mechanism, according to their functionality in the reaction, are initiation, termination, and propagation. And the steps will always be one or the other. They won't, in the same mechanism, they will not function in multiple ways. So, an initiation step, like I said earlier, is the one where the radical species is generated. So you have to have a step that occurs at the beginning that generates the radical. And so that's going to be the homolytic bond cleavage. That is just almost always the first step. You're going to have some sort of energy to cleave that bond. So it'll be heat, light, something will cleave that bond, usually heat or light. And so you see, once again, one of the electrons moves off with one X, the other one moves off the other. It's a homolytic bond cleavage. And you've seen this many, many times. This is an initiation step because this initiates the whole process. It initiates the whole reaction. Then, in a radical chain reaction, you're going to have a bunch of propagation steps. And so these different types of steps will serve to propagate the reaction. And so these four, as they're drawn here, aren't going to make any sense because you probably won't use all four in a radical chain reaction. You might just use a couple. And so as you learn these and you learn to recognize these, you'll just need to remember that these four will have a function to propagate the reaction. And so when you go in to look at your propagation reactions or propagation steps or to figure out what they are, they'll be one of these four. Okay, and you may need like this one and that one. You may need 2 or 3 of these four, probably not all 4 types in a radical chain reaction. But this will give you an idea of what you need to choose from in identifying the propagation steps of a radical chain reaction. And then at the end, the reaction will end. So the termination of the reaction will end by 2 radicals coming together to form a bond. And so this, as you can see, and this is your coupling reaction. This was number 6 in that group of 6. It was the last one. And you can see how this is going to terminate the chain reaction. Because once your radicals come together, once they bump into each other and a bond is formed here, the chain reaction is going to end because you won't have any more radicals to come to react because they'll be consumed by this sort of a reaction. And so this termination step in industry where radical chain reactions are used, this is a very undesirable thing to happen because you want to postpone this as long as possible and have as many propagation steps as possible and have, because the propagation steps, as many turnovers as you can get, and that will increase your yield of your reaction. And of course, increasing the yield of the reaction is a very desirable thing. So this is what you want to postpone if you're in industry and you use these reactions. Now, let's look at the chlorination of methane. This is one of the simplest reactions that you're going to study. The chlorination of methane, you've got, you know what methane is, you know what chlorine is. Here's the light. So the light is simply going to homolytically cleave the chlorine-chlorine bond. So this is the initiation step. This is where you initiate the radicals that will then react in your radical chain reaction. And so the overall reaction, which you must keep in mind, is the goal is to convert methane into methyl chloride and hydrogen chloride. So here the goal of this reaction is to synthesize methyl chloride. And you're going to give off hydrogen chloride. This hydrogen chloride can be removed, and so then you'll have the methyl chloride plus some impurities. So here is the first step that happens. And then next, you're going to have your propagation steps. These propagation steps will be the heart of the reaction. So you have generated the chlorine atoms, which are chlorine radicals. And so the first step is going to be a hydrogen abstraction. Remember that was number 3 in your group of 6 different reaction steps that you might have. So Cl dot comes in, that abstracts H dot, the 1 electron from chlorine and 1 electron from the CH bond form the HCl bond here, and the other electron moves back to reside on carbon. So you have methyl dot. This is a radical, and you have hydrogen chloride formed. Now remember, your products, your desired products were hydrogen chloride and chloromethane. And you can see that you are converting the reactants, which were methane and chlorine, into your products, chloromethane and HCl. So the second step is, you have to repeat this. You take the product from the first reaction, the methyl radical. Here you have the methyl radical. You have the unpaired electron on methane and on the carbon of methane. And you use one of the electrons from the chlorine-chlorine bond. It moves out. And you use the other electron coming from carbon. And you're forming this carbon-chlorine bond. And the other electron in the chlorine-chlorine bond moves out to reside on chlorine. Now, so let's look at this again. You have used, here's one of the reactants, here's your other reactant, and you're converting them to your two products. That is what your propagation steps must do. Your propagation steps must convert the reactants to the products. That's the goal of the reaction. And your propagation steps must accomplish the goal of your reaction. Okay. Now, the other thing that your propagation steps must do, and the reason I'm putting it that way is because if you're ever asked to draw propagation steps for a reaction, this is the way to check and see if you've got the propagation steps correct. Look and see if your propagation steps move the reactants into the products. And the other thing is, in order for them to be true propagation steps, whatever it is, here's the radical up here that reacts with your reactant, it has to be regenerated down here. So your radical that you needed to start the reaction is regenerated down here. So this goes back up here, and it reacts with another molecule of your reactant, and it forms, once again, the methyl radical and HCl, and then the methyl radical reacts with chlorine, your reactant, to generate your product, and Cl dot. And then Cl dot goes back up here. So what the propagation steps must do is it has to regenerate the reactant up here. Whatever the radical is that is needed to start the reaction with your reactant, whatever that radical is, it has to be regenerated down here in one of the later steps. It doesn't always have to be the last step, but usually it is the last step. And so those are the two things that you can review. If you're asked to draw the mechanism in a radical chain reaction, you can look to see if the mechanism that you're proposing converts the reactants into products, and does it regenerate the radical that is necessary to start the mechanism over again. Those are two things to check. Now, the chlorination of methane. This is drawing in equations what I just said. So here the chlorine, the chlorine is Cl dot is consumed and it's regenerated down here. Over here you can see that the methyl radical is consumed and it's regenerated up here. And so canceling those out, you can see that your reactants are converted to products, while the radicals are generated and consumed over and over and over. Each one of these propagation cycles is called a turnover. So you have a turnover there. And every time that you have the turnover, you are converting reactants to products. And so that's what makes this a chain reaction, is that it occurs over and over and over and over and over by these propagation steps. The products formed are the reactants in the next step. The products formed will be the reactant in the next step. Okay, polychlorination is difficult to prevent. So once you get the first chlorine on there, you can also chlorinate again and again and again. And if you have enough chlorine in there, you'll convert the methane all the way to carbon tetrachloride, and that'll be your only product. But usually you're not going to want to do that. Usually you'll want to stop with, say monochlorination. You usually won't want to get perchlorination in your reaction. So what they do is they will use an excess of methane. And so that just increases the odds that your chlorine will bump into methane instead of one of these. And so you can use a huge excess and just make it a statistical effect and greatly increase the probability that chlorine will react with your methane to give you your desired product. And a major problem here is that the methyl chloride is more reactive towards chlorination than methane itself. And so even whenever you use a huge excess, you'll still get some, at least, methylene chloride and less chloroform and carbon tetrachloride. You can also use radical initiators. This is what I was telling you about. So this is the what you need for the initiation step. And notice that you have here in each case, you have here you have a chlorine-chlorine bond, oxygen-oxygen bond, oxygen-oxygen bond. So this is what's called a heteroatom-heteroatom bond. Heteroatom-heteroatom, heteroatom-heteroatom. And by heteroatom, that term means something other than carbon or hydrogen. And so here, the reason that you can look for these, and they will often be a clue that you're going to have a radical reaction. When you have a heteroatom bond, that tells you, this may be a radical reaction. And the reason for that is because heteroatom bonds are usually very weak. And so it's easy to use them as an initiator step. So you cleave this bond, it doesn't take much energy. And here it doesn't take much energy, and here it takes even less energy, because down here it's so stable. Notice this is stabilized by resonance, and so it doesn't take much energy at all to cleave this oxygen-oxygen bond. And you want to use radical initiators that are easy to cleave because you don't want to cause other reactions to occur by heating up your reactants too high. And so this will ensure that you just get only the radical reaction taking place. You can also have radical inhibitors if you don't want a radical reaction to take place. And so, a lot of times people will wrap their flask in aluminum foil to keep light out. And you can also, if you add a radical inhibitor, then you also have to worry about getting it out of the reaction because it becomes an impurity. But it's still it's used. So here, the oxygen molecule is a diradical, and it's a good inhibitor. Hydroquinone is a good radical inhibitor. And so the radical reactions will either not take place, or they'll take place very slowly in the presence of these inhibitors. So hydroquinone undergoes hydrogen abstraction. So R dot, the radical that you want to prevent from reacting in your reaction, if you put some hydroquinone in there, you can quench that radical reaction, because hydroquinone will, the H dot of hydroquinone will be abstracted by R dot, and you'll get RH. And this is a very stable radical. Hydroquinone has formed a very stable radical. It's stabilized by resonance. And so then this down here can actually donate another H dot to another R dot. And here you'll have RH. So it's quenched another radical. And then you simply get this benzoquinone, which is a stable molecule. So that ends the first part of our discussion on this chapter on radicals.